So this is very strange. I'm sat in my office talking to myself, but hello everyone, my name is Ian Boutle and I'm going to talk to you today about the Met-Office Unified Model. This is something that's been developed by a cast of hundreds, maybe thousands of developers over the years, but I wanted to start by giving a shout out to Nathan Main and the Exoplanet Theory group, who are really the people responsible for taking the model of this blue planet on the right here and turning it into something that we can use to model exoplanets with. I'll start with a bit of history and philosophy of the model. So it started in 1991, therefore it's approaching 30 years old, and hopefully it will be retired within the next 5 years or so and replaced with a completely new model called Elfric. Over the 30 years, it's had 3 completely new dynamical cores of increasing complexity, and it's also had numerous physical parameterizations. The key theme running through everything, though, is this word unified. We want to use the same model for everything, for weather, for climate, and for exoplanets. The idea being that the physics of the real world is the same, so why should the model be any different? If you're representing the physics correctly, then you don't need to change it depending on its usage. In practice, I think it's the only model to get anywhere near actually achieving this, and there are still the occasional differences between different modelling setups that we run. So just to run through what we currently use the model for, we'll start at the low resolution, sort of hundreds of kilometre grid scale, what's the climate simulations, the kind that we're running for CNIP 6. We kind of then step down an order of magnitude to your kind of tens of kilometre grid length. These are the simulations that we run every day for our global numerical weather forecasts and out to kind of seasonal scale forecasting as well. And then we can step down another order of magnitude or two to the hundreds of metre scale where we run very high resolution detailed forecasts for city scale forecasting and bespoke weather events. So this example here is one from the sailing events of the 2012 Olympics, showing the Weymouth Harbour area where these events were held. What we can then do is we can apply all of this to exoplanets. So this is a plot here from Dennis's paper, which he'll probably talk more about in his own talk, where you've got the kind of the climate model scale representation of a tidally locked planet orbiting an M dwarf around the edge here, and then over the hotspot you've got the high resolution detailed simulations of the convection permitting grid. So I'll spend the next few slides talking through the key components that make up the model, the first of which obviously is the dynamical core, which is called endgame. One of the useful aspects of this is it has a semi-implicit time-stepping structure which gives accurate, so by that I mean non-diffusive but stable results. And this can really be seen in these 2 plots at the top here, one showing a satellite picture of the UK and the other showing model simulations from our operational UK forecast model running with a 1.5 kilometre grid length. And the feature of interest are these kind of long banded structures in the clouds, which are lee waves that form as the air flows over a mountain and then they kind of propagate downstream of the mountain. And what you can see is that the model actually can really represent these lee waves very well. And this is a kind of feature that models typically struggle with because the numerical diffusion, which is typically implicit within the model to keep it stable, often smooths out these features so that they don't exist. The other key aspects of the dynamical core are semi-Lagrangian advection scheme, which is good to give the model long time step stability. Hopefully means it can run a bit faster. It uses a compressible non-hydrostatic equation set, which is good for modelling explicit convection, as I showed in Dennis's plot on the previous slide. And finally, it uses the full deep atmosphere equations, which hopefully means it's accurate in all regimes. And this is what these 2 plots at the bottom show, something Nathan will talk about more in his presentation, but it's showing the jet structure from 2 otherwise identical simulations of a tidally locked planet, one using the deep equation set and the other using the primitive equation set. And what you can see is quite a big difference between the 2. Because hopefully we believe the deep atmosphere equations more, but who knows what the truth actually is here. So the next thing to talk about is radiation. The scheme is called Socrates, and this represents the gaseous continuum, cloud, and aerosol absorption and scattering using a correlated K method. The scheme uses a two-stream approximation within each grid box, so you have an upwelling and a downwelling beam, but there is actually a parameterization of spherical geometry detailed in Stefan's paper. And what this means is we can actually direct output of transmission spectrum from the model. So we call the radiation scheme primarily using broadband spectral files like any other model to calculate the heating rates, but we can do a secondary diagnostic call to the radiation scheme using a very high resolution spectral file, and then use this to create reflectance, emission or transmission spectra where the radiation is seen with the exact same model state as the model itself has internally. And so that's what's kind of shown on the right here. There's an example of a reflection spectra and a transmission spectra of Proxima b generated directly from the model. It's also worth saying that this is the same scheme that is used in Rocky 3D, so hopefully we can do some good comparisons there. The next thing to talk about is the surface setup. So this scheme is called Joules. For the tie experiments, I've just used a simple slab surface. So this just has a configurable albedo, heat capacity and resistance to evaporation in a one-layer model to simulate the land or sea surface. But Joules has the ability to have more complex tiled and layered surfaces, including multiple vegetation categories, lake, soil, ice, urban areas. We've only really used bare soil on exoplanets so far, and this plot on the right here is from Neil's paper showing kind of as you increase the size of a continent at the hot spot, this was using the bare soil parameterization of Joules, how it kind of feeds back onto the hydrological cycle as you start to remove water from the atmosphere and progressively get less cloud. I should say that we also have the option for resolved and subgrid orography, which we haven't used on exoplanets yet. And also there is the possibility of a coupled ocean model called NEMO that we use for Earth climate simulations, but again, haven't tried on exoplanets just yet. So we move from the surface up to the turbulence and convection parameterizations. And I always think the best way to understand what these do is to kind of visualize how the atmosphere looks as you move from cold regions like the pole or the night side of a tidally locked planet down towards warm tropical regions or the hotspots of a tidally locked planet. And so in your cold places, we just have a potential temperature profile that increases with height. And so here the turbulent mixing is parameterized by a first order down gradient K diffusion approach. As you start to introduce some cloud to this, you get turbulent mixing driven from the cloud top. That's where we have explicit parameterizations of the entrainment at the cloud top and the non-local mixing throughout the depth of the cloud, driven by this negatively buoyant turbulent flow that leads to a well-mixed temperature profile in the cloud layer. As you then start to heat the surface, you get a well-mixed temperature profile throughout the depth of the boundary layer, and that's when you then start to introduce a non-local or counter-gradient term to describe this surface-driven turbulent mixing. As your surface then continues to get warmer, there's no reason that the cloud and the surface-driven mixing have to overlap, and so they can gradually begin to separate, and ultimately this is when you start to trigger moist convection, which is parameterized by a mass flux scheme for cumulus clouds, implicitly coupled to the boundary layer scheme, so that ultimately you get to this kind of tropical deep convection where you have the most of the atmosphere is treated by this mass flux scheme, and you only have the turbulent scheme parameterizing a small amount of the atmosphere near the surface. Once you have some cloud, you need to know what to do with it, and that's primarily the job of the microphysics parameterization. So the UM has a prognostic treatment of liquid and frozen condensate and fraction, and the plot on the right is there to do nothing but confuse you about the complexity of the microphysics scheme, but the idea is that you're trying to physically represent the transfer of water between these different categories, so how it moves from water vapor into cloud droplets or ice or snow or rain and all of the different processes that move from one to the other. And the result of this is that you can support things like supersaturation with respect to ice, very low temperature liquid, etc. You can get a much bigger variety of cloud properties than you get with a simpler scheme that has kind of a temperature dependent threshold or something like that. And the final thing to say is that there is a consistent treatment of optical properties in the radiation. So there's some pictures of ice crystals here to show how they differ, and that obviously reflects light very differently. And so how the optical properties are calculated is consistent with how all these process rates operate within the microphysics scheme to process the cloud. And then the final thing to talk about is the other kind of stuff that we have going on. So we have UKCA, which is an interactive chemistry and aerosol scheme. And so one of the things this has been used to look at is ozone, paper by Jack Yates, where he's looking at quiescent ozone only on an M dwarf, shown on this top plot for the column integrated ozone. And as you can see, it all kind of seems to collect on the night side of the planet, where it's coldest. What we're currently looking at is adding flares to this to see how that might affect the ozone evolution. The other thing we've looked at is mineral dust. So this is dust lifted off the planet's surface if it's a rocky planet. A paper of mine earlier this year showed how having this dust affected around in the atmosphere cools the day side and warms the night side of the planet, so potentially increasing the habitable zone. And also making your transmission spectra look very difficult to interpret because they're full of dust. There's a lot more to explore here as well. And then ongoing work I just wanted to mention was trying to couple this model to COPS and ExoGaia to look at the geochemical and biogeochemical cycle for early life of this planet. And then there's a whole plethora of other work on hot Jupiter, clouds and chemistry, various papers by Stefan and Ben that I haven't had time to talk about. So the final things to kind of talk about are, is it any good? Well, for this planet, yes. It's consistently ranked as one of the top NWP models out there. The plot on the right shows the performance of the Microphysics model against other key NWP models around the world, from the US, France, Japan, Canada, Germany, Korea, and they're kind of normalized by our own performance, but basically up is better. So it shows that over the last 5 years or so, we've been the top performing model. We also benchmarked very highly against key observational climate constraints in the climate model perspective as well. But that doesn't really mean anything for exoplanets. Nathan did a paper, probably the first paper using the UM for exoplanets, where he benchmarked it against a range of dry dynamics tests from the Hem et al. Paper for both Earth-like setups and at the top here and hot Jupiters in the middle. And I think they showed quite good comparison, actually. And then at the bottom here, a range of papers by David Amundsen benchmarked the radiative transfer scheme against line-by-line codes, shown on the left here, performing quite well, and on the right against using the full model to model HD209. And again, it shows quite a reasonable comparison to what observations we have. So it's not bad, I think. But the final question Thomas said was, could you put a slide on where could it be unreliable? So I thought I'd say three things here. The first of which is it is possibly overtuned for this planet. There are many empirical aspects to parameterizations which are derived from observation rather than fundamental theory. But it's difficult to remove these without reducing the accuracy of the model. So I think you're always going to have a trade-off between having a model which is very accurate and a model which is very generic, and how you pitch the link between the two is difficult. The second thing is worth saying is stability. The lack of numerical diffusion makes it good for accuracy, but it does make it quite tricky to run at times. It falls over very easily. And the height-based vertical coordinate can, particularly on hot Jupiters, lead to large pressure gradients, and you get wave breaking near the poles, which again causes it to fall over very easily. And then the final thing I wanted to say was conservation. This is primarily a problem with the semi-Lagrangian vector scheme, is that mass, moisture and energy all require post hoc fixing to enable them to be conserved. And in fast hot Jupiter simulations, we've seen loss of angular momentum as well, which is not ideal. So that's all I really wanted to say. If you have any questions, I won't answer them live because I'm in New Zealand and I'll be asleep, but I'm sure Nathan and Dennis will do their best, or if not, I can answer stuff via email. Thank you all for listening.